What I want to do in this video is review much of what we've already talked about, and then hopefully build some of the intuition on why we divide by n minus 1 if we want to have an unbiased estimate of the population variance when we're calculating the sample variance. So let's think about a population. So let's say this is the population right over here, and it is of size capital N. And we also have a sample of that population. So a sample of that population, and at its size, we have lowercase n data points. So let's think about all of the parameters and statistics that we know about so far. So the first is the idea of the mean. So if we're trying to calculate the mean for the population, is that going to be a parameter or a statistic? Well, when we're trying to calculate it on the population, we are calculating a parameter. Calculating a parameter. So let me write this down. So this is going to be, so for the population, we are calculating a parameter. It is a parameter. And when we attempt to calculate something for a sample, we would call that a statistic. So how do we think about the mean for a population? Well, first of all, we denote it with the Greek letter mu, and we essentially take every data point in our population. So we take the sum of every data point. So we start at the first data point and we go all the way to the capital Nth data point. So every data point we add up. So this is the ith data point. So x sub 1 plus x sub 2 all the way to x sub capital N. And then we divide by the total number of data points we have. Well, how do we calculate the sample mean? Well, the sample mean, we do a very similar thing with the sample, and we denote it with a x with a bar over it. And that's going to be taking every data point in the sample, so going up to lowercase n, adding them up. So these are all the sum of all the data points in our sample, and then dividing by the number of data points that we actually had. Now, the other I guess, thing that we were trying to calculate for the population, which was a parameter, and then we'll also try to calculate it for the sample and estimate it for the population, was the variance, which was a measure of how dispersed or how much the data points vary from the mean. So let's write variance right over here. And how do we denote and calculate variance for a population? Well, for a population, we'd say that the variance, we use the Greek letter sigma squared, is equal to, and you could view it as the mean of the squared distances from the population mean. But what we do is for each data point, so I equal 1 all the way to n, we take that data point, subtract from it the population mean. So if you want to calculate this, you'd want to figure this out. Or that's one way to do it. We'll see there's other ways to do it where you can kind of calculate them at the same time. But the easiest or the most intuitive is calculate this first. Then for each of the data points, take the data point and subtract it from that. Subtract the mean from that. Square it. And then divide by the total number of data points you have. Now we get to the interesting part. Sample variance. There's several ways where when people talk about the sample variance, there's several, I guess, tools in their toolkits, or there's several ways to calculate it. One way is the biased sample variance, the non-unbiased estimator of the population variance, and that's usually denoted by S with a subscript n. And what is the biased estimator here? How would we calculate it? Well, we would calculate it very similar to how we calculated the variance right over here, but we would do it for our sample, not our population. So for every data point in our sample, so we have n of them, we take that data point, and from it we subtract our sample mean. We subtract our sample mean, square it, and then divide by the number of data points that we have. But we already talked about in the last video, how would we find what is our best unbiased estimate of the population variance? This is usually what we're trying to get at. We're trying to find an unbiased estimate of the population variance. Well, in the last video, we talked about that if we want to have an unbiased estimate, and here in this video, I want to give you a sense of the intuition why, we would take the sum. So we're going to go through every data point in our sample. We're going to take that data point, subtract from it the sample mean, square that. But instead of dividing by n, we divide by n minus 1. We're dividing by a smaller number. We're dividing by a smaller number, and when you divide by a smaller number, you're going to get a larger value. So this is going to be larger. This is going to be larger. This is going to be smaller. And this one we refer to the unbiased estimate. Unbiased estimate. And this one we refer to the biased estimate. Biased estimate. If people just write this, they're talking about the sample variance. It's a good idea to clarify which one they're talking about, but if you had to guess and people give you no further information, they're probably talking about the unbiased estimate of the variance. So you would probably divide by n minus 1. But let's think about why this estimate would be biased, and why we might want to have an estimate like this that is larger. And then maybe in the future we could have a computer program or something that really makes us feel better that dividing by n minus 1 gives us a better estimate of the true population variance. So let's imagine all of the data in a population, and I'm just going to plot them on a number line. All the data. So this is my number line. This is my number line. And let me plot all of the data points in my population. So this is some data, this is some data, here's some data, and here is some data here. And I can just do as many points as I want. So these are just points on the number line. Now let's say I take a sample of this. So this is my entire population. So let's see how many I have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So in this case, what would be my big N? My big N would be 14. Big N would be 14. Now let's say I take a sample, a lowercase n of, let's say my sample size is 3. I could take, well, before I even think about that, let's think about roughly where the mean of this population would sit. So the way I drew it, and I'm not going to calculate it exactly, it looks like the mean might sit someplace roughly right over here. So the mean, the true population mean, the parameter is going to sit right over here. Now let's think about what happens when we sample. And I'm going to do just a very small sample size just to give us the intuition, but this is true of any sample size. So let's say we have sample size of 3. So there is some possibility when we take our sample size of 3 that we happen to sample it in a way that our sample mean is pretty close to our population mean. So for example, if we sampled that point, and that point, I could imagine our sample mean might actually sit pretty close to our population mean. But there's a distinct possibility. There's a distinct possibility that maybe when I take a sample, I sample that, and that. And the key idea here is when you take a sample, your sample mean is always going to sit within your sample. And so there is a possibility that when you take your sample, your mean could even be outside of the sample. And so in this situation, and this is just to give you an intuition, so here your sample mean is going to be sitting someplace in there. And so if you were to just calculate the distance from each of these points to the sample mean, so this distance, that distance, and you square it, and you were to divide by the number of data points you have, this is going to be a much lower estimate than the true variance from the actual population mean, where these things are much, much, much further. Now, you're always not going to have the true population mean outside of your sample, but it's possible that you do. So in general, when you just take your points, find the squared distance to your sample mean, which is always going to sit inside of your data, even though the true population mean could be outside of it, then or it could be at one end of your data, however you might want to think about it, you are likely to be underestimating the true population variance. So this right over here is an underestimate. And it does turn out that if you just, instead of dividing by n, you divide by n minus 1, you'll get a slightly larger sample variance, and this is an unbiased estimate. In the next video, and I might not get to it immediately, I would like to generate some type of a computer program that is more convincing that this is a better estimate. This is a better estimate of the population variance than this is.